Science Lesson 7, Up and Down Quarks. Today we're going to be learning what a quark is. We're going to be looking at two of the three quarks you need to know about, the up quark and the down quark. So, what is a quark? Quarks are what make up the big, heavy particles that we find inside a nucleus, protons and neutrons. Now you might not think protons and neutrons are that heavy. They're comparatively light compared to pens or jumpers. But they're much, much more massive than things like electrons, which we call leptons, or mesons, which we haven't got to but are also quite small. Baryons are the biggest particles, and they have three quarks in them. And the two baryons you need to know about are the proton and the neutron. The word baryon actually comes from the Greek word for heavy. And it's also what gives us the word barometer, one of those strange machines where the mercury goes up and down depending on the weather. The idea is that it's measuring how heavy the air is. The element barium also gets its name from this root, because barium sinks in most liquids. It's denser than water, so it sinks to the bottom, and so they call it the heavy element. So whenever you think baryon, think lots of mass, very, very big. So, protons and neutrons are made up of two different quarks, the up quark and the down quark. They both have the same mass, the up quark and the down quark, and that mass is exactly a third of a proton or a neutron. Well, it's actually a little bit less. We'll get to that later. For now, it's a third. The charge on them, though, is what's interesting. The charge on up quark is plus 2/3, and the down quark is minus 1/3. Now remember, this is not in coulombs. This is relative charge in the same way that a proton has one relative charge and an electron minus one. These are fractions of a coulomb, but it's far more sensible to just talk about the relative charge. So, how can we make a proton out of these two quarks? Well, that's very simple. If we have an up quark, and a down quark, well, that will be plus 4/3 minus 1/3, giving us a charge of plus 1. So a proton is made of an up quark, and a down quark. On the flip side, a neutron is made up of an up quark, a down quark, and a down, because then we've got plus 2/3 minus 1/3 minus 1/3, giving us our charge of 0. Easy. So we've looked at now at beta plus and beta minus decay. Remember, in beta minus, a neutron is turning into a proton. So if we're going from a neutron to a proton, well, what's actually happening inside is that a down quark is changing to an up quark. On the flip side, in beta plus decay, we've got a proton turning into a neutron, which means an up quark is actually turning into a down quark. So what's really happening during this beta plus beta minus decay is that one quark is changing. Now, we call these two things, up and down, flavor. The reason for this is when they first discovered quarks, they actually named them after ice cream. So we had strawberry quarks, chocolate quarks, vanilla quarks, because they didn't know what else to call them. And this word, the flavor of quark, remains. So you can say a quark has a flavor of up or a flavor of down. And what's going on here is these quarks are changing flavor. The way they do that is through, well, we've met the strong force, which binds the nucleons inside the nucleus. This is through the weak force, also often called the weak interaction, because is it really a force? Hard to tell. So this happens because of the weak interaction. Because of the weak interaction, quark changes flavor, and that's how we get our two different types of beta radiation. Now, there's one more thing I want to touch on today, which is something called baryon number. We talked a couple of lessons ago about lepton number and how that is always conserved. And remember, the electron-lepton number is conserved separately to the muon-lepton number or whatever other lepton number. Now, baryons are not so strict. There is just a thing called baryon number, and it's always conserved. protons and neutrons have a baryon number of 1. This means that whenever you've got a proton on one side, you're going to need a proton or a neutron on the other side after your decay has happened, so that baryon number is conserved, which is fine. During beta minus and beta plus, we've got baryon number of 1 here into a baryon number of 1. Same here. This, of course, means that the baryon number of each of these quarks is a third. So a third plus a third plus a third, baryon number of 1. The inverse is true of all the antiparticles. So a proton has a baryon number of -1. Sorry, an antiproton has a baryon number of -1. An antineutron has a baryon number of -1. An anti-up quark, because of course an antiproton is going to be made of an anti-up, anti-up, anti-down. An antineutron is going to be made of anti-up, anti-down, anti-down. They all have a baryon number of -1/3. And the charges are clearly going to be flipped. So if we have an anti-up, that's going to have a charge of -2/3, and an anti-down will have a charge of +1/3. Exactly the same as any other antiparticle, the mass stays the same, but the charge flips. So if we're thinking about antiproton, well, that's going to be made up of an anti-up, an anti-up, an anti-down. So that's therefore going to have a total charge of -1, because it's -2/3 add -2/3 add +1/3, giving us a total charge of -1. Same is true of an antineutron, anti-up, anti-down, anti-down, still ends up at a charge of 0. Baryon number of an antiproton, -1. And remember, baryon number is always conserved. Does this work when we're thinking about annihilation? Yes, of course it does. For proton, baryon number 1, it's an antiproton, baryon number -1. That means the total baryon number before we start is 0. They annihilate into a photon. Photon doesn't have a baryon number, so we remain at baryon number 0. Same is also true when we create matter. High energy photon, baryon number 0, splits into proton, antiproton, 1, -1, therefore overall 0. So you can see that both the decaying, the annihilation, and the production of matter all obey this conservation of baryon number. That's all for this week. Enjoy your half